All right, for this lesson, we're going to be looking at relations and functions. So, a couple of notes here past the warm-up. A function is a special type of relation. It relates an input with an output. For example, if my input was the number of gallons of gas, then my output would be the amount paid to fill up the tank. The domain is the set of valid inputs, or the x's, and the range is the set of valid outputs, the y. And we can represent functions in a lot of different ways. You can do it verbally, numerically, symbolically, and graphically. So let's take a look at the first example. It says graph the function, the absolute value of x, by hand. So this is the first type of representation of a function symbolically, so algebraically. Verbally, I could say it exactly as I just said it, the absolute value of x. The function is the output of the input of the absolute value of x. And so now let's do this numerically, and that means using a t-table. So what I'm going to do is I'm going to come up with a set of values, so x and f of x. And by doing that, let me pick some values as my input. And so let's just simply use the numbers -2, -1, 0, 1, and 2. And so then what will be my output? Well, the absolute value of -2 is 2, the absolute value of -1 is 1, the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of 2 is 2. So numerically, I've just represented that function as well. And then the last representation is, of course, graphically. So what does this function look like? You know, they always say a picture is worth 1,000 words, so it's always good to sometimes look and see what this image looks like. And so if I do that, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, and so that would be that graphical representation. And it almost appears to be two linear functions. In fact, we'll get into the definition of piecewise functions eventually. But so there's all four representations right there. Now, the formal definition of a function is a relation in which each element in the domain corresponds to exactly one element in the range. In other words, the domain should not repeat with any different range values. So, for example, it says let a function f be defined by f of -1 is 4, f of 0 is 3, f of 1 is 4, f of 2 is -2. Now, notice that the inputs are -1, 0, 1, and 2. The outputs are 4, 3, 4, -2. You might be thinking, oh, look, the 4 and the 4 repeat. Well, that doesn't matter. Oh, I made it look Christmassy with red and green. Anyway, that doesn't matter, right? The definition is the range can repeat. What cannot repeat in order for it to be a function is the domain. And so keep in mind the domain values were -1, 0, 1, and 2. None of those values repeat with any other different range values. So yes, this would be a function. Now, if we write it as a set of ordered pairs, the first ordered pair would be -1, 4. The second ordered pair would be 0, 3. The next ordered pair would be 1, 4. And the last ordered pair would be 2, -2. So there are my set of word pairs. And then it says give the domain and range. The domain, it would be the numbers in red, and the range would be the numbers in green. All right, example 3 says the function f computes the revenue in dollars per unique user for different technology companies. This function is defined by f of a equals 189, f of g equals 24, f of y equals 8, and f of f equals 4, where a is Amazon, g is Google, y is Yahoo, and f is Facebook. Amazon apparently makes the most dollars per user. Okay, for part A, it says write f as a set of ordered pairs. So the first ordered pair would simply be A for Amazon and 189. The next would be G for Google with 24. The next one would be Y for Yahoo, which would be 8. And the last one would be F for Facebook at 4. So to give the domain and range of F, the domain would be the input, the X values, A, G, Y, and F. So that would be the domain. The range would be the Y values, or the outputs, which would be 189, 24, 8, and 4. It says interpret f of a equals 189. So now let's actually, what does that actually mean? So f of a equals 189, that means that the revenue in dollars per unique user for Amazon is $189. That's what that interpretation is. All right, example 4, it says let the function x over x minus 1 be f of x. It says, if possible, evaluate f of 2, f of 1, and f of a plus 1. So let's start off with f of 2. F of 2 would give me what? Let's see, I'd have 2 over 2 minus 1, which would give me 2 over 1, which would give me 2. So f of 2 is 2. Let's see, f of 1 would give me 1 over 1 minus 1, which would be 1 over 0, which is undefined or does not exist. The function, because you can't divide by 0, we know that. And then f of a plus 1 would be a plus 1 over a plus 1 minus 1, which would end up being a plus 1 over a. And the a's do not cross out, just for the record. Don't be tempted to say that. That's algebraically incorrect. I mean, for example, we know that 3 plus 4 divided by 3, that is not just 4. You can't just cross out those 3's. That would be 7 over 3. So we know that's not to be true. So don't do that with the algebra. Remember, algebra is just simply a generalization of your numerical numbers. So don't do that. All right, it says find the domain of f. So if you remember from Algebra 1, the way that you find the domain of a rational function is you have to see if there are any places where the denominator equals 0, and we found that out already. The only place that would make the denominator equal to 0 is when x is equal to 1. The function does not exist. So we want to write out an interval notation that describes that. So when we're talking about the domain for this function, the domain would be, we don't want to include 1, so it would be from negative infinity to 1, but we wouldn't include it, so we put a parenthesis there, union 1 to infinity. So it's like you're picking up your pencil, right? This says that we're not including the number 1. It's like we're getting to 1, but we don't include it. We pick up our pencil and then we kind of like jump a gutter and then keep on going. So this is what we call interval notation. Secular notation would be like if you would say it's x such that x cannot equal to 1, and that's this would be set builder notation, and the other one would be interval notation. Now we show both because you can write it both ways, but more often than not, I'm going to use interval notation because that's my preference. That's the one I like. But just to reiterate, to find the domain for a polynomial function, which we're going to talk about those also, it's all real numbers. Typically, the only times you have to be on the lookout for issues with the domain is if you have a rational function or if you have a radical function like a square root. All right, so for example 5, it says, let g of x equals x squared minus 2x. Graph the function using a graphing calculator. Find the domain and range of g. Use interval notation. Use g of x to evaluate g of negative 1. And use the graph of g to evaluate g of negative 1. All right, well, let's just start off with part B, and then we can use a graphing calculator for parts A and C. So it's use g of x to evaluate g of negative 1. So if I plug in negative 1, I'd have negative 1 squared minus 2 times negative 1, which looks like I'd end up getting 1 plus 2. So I should get 3. All right, so now let's use the graphing calculator to graph it. So it's x squared minus 2x. So I'm just going to type in x squared minus 2x, and there's my graph. So talking about the domain, first of all, remember the domain is the input of the x values. For a polynomial function, which this is, it's a quadratic, the domain is all real numbers. Remember, the two things you have to look out for with domain are rational functions, because you don't want the denominator equal to 0, or radical functions, because we can't have the square root of a negative number. This is neither case, so the domain is just all real numbers, so it goes from negative infinity to positive infinity. The range is different, though, because the range is how low, right? It's the y values, and the y value, that's the y-axis, so how low to how high it goes. If you notice the graph, the graph of the function goes no lower than -1, but it does keep on going up indefinitely, all right? So that means it's going to continue to increase to infinity. And so that will be the domain range. And then it goes on to say, well, what's the value of, g of -1? Well, one way you can do that is you could hit Menu, Trace, Graph Trace, and just simply put in -1 and hit Enter. And as we got 3 earlier, there's 3 in the bottom right-hand corner. All right. For example 6, it says let f of x equal the square root of x minus 1. Graph the function using graphing calculator. It says evaluate f of 1, find the domain range. All right, so let's go back to our calculator. Square root of x minus 2. So I'm going to just hit escape, tab. I'm going to clear this out. Square root of x minus 2. Square root of x minus 2. Okay, and let me just double check that's correct. Yep, it is. All right, so it says for the first part, evaluate f of 1. Okay, so if you look at the graph, here is 1, but if you notice, the graph of the function doesn't start until what number? 2. So I bet if I hit Menu, Trace, Graph Trace, and type in 1, why do you think the calculator says undefined? The reason is because the function does not exist there, correct? So what we have here is, talking about the domain anyway, 1 is not a part of my input. 1 is not a part of my domain. Also remember, the domain of a polynomial function is all real numbers, but this isn't a polynomial function, this is a radical function, right? So a radical function, we can't have the square root of a negative number, right? We can't take the square root of a negative number. There's no real number that occurs. So the way that you find the domain algebraically for this is you simply take what's in the radical and you set that to greater than or equal to 0. Because you need that to be greater than or equal to 0. If you solve this, you get x is greater than or equal to 2, which means that my domain would have to be numbers that are greater than or equal to 2. So that means my domain would include the numbers 2 and increase without bounds. So that would be my domain. The range for this function would be how low it goes. Well, if you notice, the function does not continue going down without bound. It stops at a y value of 0. So then my range would be from 0, 0 is included, and it continues to increase without bounds, so 0 to infinity. And that would be the domain range describing those for that particular function. All right, example 7. Says when the relative humidity is less than 10%, air cools at a rate of 3.6 degrees for every 1,000 foot increase in altitude. Give verbal, symbolic, graphical, and numerical representation of function f that computes this change in temperature for an increase in altitude of x thousand feet. Let the domain of f be from 0 to 6. Okay, so when the relative humidity is less than 10%, air cools at a rate of 3.6 degrees for every 1,000 foot increase. So for every 1,000 foot increase, it's cooling. It's decreasing at a rate of 3.6 degrees Fahrenheit. So verbally, that's me saying it. Symbolically, I could do it wants to be a function. So f of x would be equal to negative 3.6 x. And so that means for every 1 increment, right, it's going to decrease negative 3.6 degrees Fahrenheit. So there's my symbolically. Numerically, all right, from 0 to 6, if I want to do that, well, of course, if there is no change in altitude, then that means nothing should occur temperature-wise, so that would just be 0. But if there's 1,000 foot increase in altitude, that means it's going to go down negative 3.6. If there's a 1,000 decrease, that would be negative 7.2. And even though I'm running out of room, you could continue on up to an input of 6. So maybe I can do a couple of more, but they're not going to be, under each other. So let me put it right here. So 3, all right, 3, that would be 10.8. negative 10.8. Then 4 would be negative 14.4. 5 would be 18, and 6 would be 21.6, both of those being negatives. So it's decreasing. So graphically, what this would look like would be, let's do an axis, and so this will be X, which will be, 1,000-foot increments, right? Very important that you label, right? And then Y would be the temperature decrease. So it really probably should have been better for me to do it more like this, which is plausible, like that, yeah. All right, and so then let's see 0, 1, 2, 3, 4, 5, 6, and let's just go in increments of 5. So 5, 10, 15, 20. All right, and so then I'm just going to do some points. So the first one is at 0, 0. The next one is at 1, negative 3.6, and then at 2, negative 7, and then 3, negative 10, and then 4, negative 14, and then 5, negative 18, and then 6, negative 20. And so you see that linear pattern going on. Clearly, though, my function would not be continuous. It would not continue going because this is specifically on the interval from 0 to 6, so I just want to include those values. But that will be my representations for that function. All right, for example 8, it says determine if each set of ordered pairs represents function. For part A, look at the domain, negative 2, negative 1, 0, negative 2. The domain does repeat with different y values, see 3 and 4, so this would not be a function. For B, 1, 2, negative 3, negative 1, 0, none of the domains repeat, so that is a function. The vertical line test, remember, states that to test graphically whether or not a relation is a function is if you can draw a vertical line and the vertical line only touches the graph only once, then it passes the vertical line test, so it is a function. A quadratic function, remember, makes a parabolic shape, either opening up or opening down. Regardless, if you do the vertical line test on that, each vertical line only touches the graph once, so it does pass, as opposed to a circle. Vertical line would not pass because it touches the circle twice. All right, and then for the last example, for example 10, it says evaluate each function for the given value. So like for example, f of negative 4, you literally just plug in negative 4 in for x, and so then if I did that, what you would get is a big number, negative 192, and then minus 112 plus 8, and then if I do that, negative 192 minus 112 plus 8, that looks like it gives me negative 296. For the next one, g of 9, 9 times 6 is 54, minus 77, that gives me the absolute value of negative 23, which is 23, so that's good. For the next one, h of a, well, that would just simply be 3a to the 7th minus 10a to the 4th plus 3a minus 11. That's not too bad. And then for the last one, plug in c minus 5. This one's tricky. You'd have c minus 5 squared minus 7 times c minus 5 plus 4. And of course, we'd want to simplify this, so I would get c squared minus 10c plus 25 minus 7c plus 35 plus 4. Combining a lot of times, so I get c squared minus 17c plus 64 appears to be the answer, right? 25 plus 35 is 60 plus 4, 64. And that's it for this lesson.